last time we learned all the definitions, the labels, the names for these various pairs of angles that we get when we cut two parallel lines with a transversal. We create 8 angles, 4 pairs. We learned the names for all those pairs last time. Now we're going to prove some results, except for this one, which was listed as a postulate. Two parallel lines are cut by a transversal, and the pairs of corresponding angles are congruent. Well, check it out. We got this line here. Let's see here. I know what I should do. Now we know which are the corresponding angles. They're in a sense, they look like they'd be the same because we have this parallel line here, right? Now, what's the difference between this line and this line? Well, if they're parallel, that means you just shifted them one way or another, but it's like a rigid movement. You didn't rotate the line in either way, you just shifted it. Like this. Let's try it this way. Well, what I'm getting at, not saying it very well, is that since there's the only difference between this line and this line is the fact that it's shifted up a little bit. As it crosses this line here, it kind of makes sense that it would cross at exactly the same angle. But let's take a look. Suppose I take this section here and move it. What do I get? Well, it just fits right over it perfectly, doesn't it? And it makes sense that it would, this angle right here. There's nothing left over. It's not too wide, it's not too narrow. It's exactly the same. And why? Well, like I said, there's hardly any difference between these two lines, except for their position. They're not rotated. So when this line cuts the transversal, it cuts it exactly the same way this one does. And that is the basis of this postulate. I'm just trying to convince you that it makes sense, if it doesn't already. But if you're willing to accept that this makes sense and believe in this postulate, we can prove a whole bunch of other relationships here. If we combine them with some of the things we learned in previous sections. For instance, remember vertical angles? These opposite pairs here, these two are vertical angles, and these two are vertical angles. And what do we know about vertical angles? They're congruent, right? And let's label all these and see what happens. I'm going to label them just a little bit different. If this is A, and we'll call this A prime. And I'll say this is B. And this is B prime. Now they just told us that corresponding angles are congruent. So the first thing I'm going to have to do is change my mind. I'm going to call these A and A sub 1. This is B and B sub 1. Why? Yeah, why not? When I get all done, you'll see why I'm doing this. Now, these two are equal because they're vertical angles. These two are equal because they're vertical angles. What about down here? Well, this angle is equal to this one because they're corresponding angles. I'm going to call that A2. Now, this angle must be equal to this one because they form a corresponding pair. So I'll call that B2. These two angles must be equal because they're vertical angles. Pardon me, they're congruent. Don't let me get by with that. They're congruent. B2 A2 is congruent to this one over here, which is B3. And this angle would be congruent to A2. We'll call it A3. So what do we have? Well, altogether, we actually have only two distinct angles, A and B. I label them this way to quickly see that all the A's are congruent, all the B's are congruent. So you see what we've got here? And we did this just by, in a sense, just fill in the blanks. We started with these two and a knowledge of vertical angle pairs. And that's all we really needed to lay this whole thing out. But this isn't a two-column proof, is it? No, it's not. It's just a really easy way to remember what the heck's going on. If you can't remember alternate interior angles, alternate exterior angles, corresponding angles, and on, this is an easy way to either remember it or rederive it. Because all you do is make use of the vertical angles here. Boom, 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 boom. And your one postulate, which says that corresponding angles are congruent. Once you've got that, you combine the vertical angles with the corresponding angles postulate, and you have every single angle mapped out. The interesting thing about this is, check this one out. These are the only two distinct angles. And what can we say about these two? Well, they form a linear pair, don't they? So, given this setup here, if you wanted to know every single one of these 8 angles, you only need one. If I know the measure of angle A, then I can work out the measure of angle B. Because they form a linear pair, the linear pair has to add up to 180 degrees. If I know this one, I just subtract it from 180 and I've got this one. When I've got these two, I've got everything else. You see how easy that is? So I'm going to start by proving the alternate interior angles theorem in the two-column proof format because, well, that's what you're going to see on the standardized exam. It doesn't hurt to practice this stuff. So let's prove this one here, the alternate interior angles theorem in the two-column proof format. Well, we're not given too much other than that we have two alternate interior angles. Never hurts to write down what it is you're intending to prove. It's kind of like keeping your eye on the ball. If you've got this written down as you're listing your statements and your justifications, you know what it is you're working towards. You don't want to lose sight of what it is you're actually intending to prove. Now in this case, it's really an easy proof. I think the first thing we can do is go ahead and use our corresponding angles postulate and write that angle 5 is congruent to angle 1. So what do we have here? Angle 5 is congruent to angle 1, and that's the corresponding angles postulate. What else do we know? Well, how about angle 4 is congruent to angle 1 because they form vertical angle pair, which we already know are congruent. Now we have angle 5 is congruent to angle 1, angle 4 is congruent to angle 1, so we have angle 5 is congruent to angle 4. And that would be the transitive property of congruence. And that is, sometimes at the end of a proof you'll see QED. That's Latin. It stands for quid erat demonstratum. It means that which was to be proved. So at the bottom of a proof, especially at paragraph proofs, the last thing you'll frequently see is that, meaning we're all done. And we are all done. See how easy that was? There's really not much to this, which explains why I was able to lay this out for you so quickly and easily as a memory device, a way to quickly lay this out. Anytime you forget, just lay this out real quick and you can jog your memory as to which angles are congruent and which ones aren't. But even the ones that aren't congruent are related. We're going to show that in just a minute. But to be complete, I really should prove this one, shouldn't I? Now, we're going to prove this one, alternate exterior angles theorem. And I think we can do this almost exactly the same way, after all. Once again, we have our corresponding angles postulate, which tells us that angle 1 is congruent to angle 5. I'll just write that down. Angle 1 is congruent to angle 5. And that is our corresponding angles postulate. What else? Well, angle 8 is congruent to angle 5, isn't it? Why? Once again, they form a vertical pair. And so, once again, all we have to do is use our transitive property and write that angle 1 is congruent to angle 8, and that's the transitive property of congruence. Notice we used the same, exactly the same thing right down the line. Very easy proofs. This next one here is what I was talking about when I said that even the pairs that aren't congruent are still related. And they are related in the sense that they're supplementary. In other words, they add up, remember, they add up to 180. And that's pretty easy to prove also. We'll do that. So what we have to do is prove that these two consecutive interior angles are supplementary. Well, I just wrote in this one angle. I think it's the only one we're going to need, but we'll see. Angle 3 and angle 6 are congruent. That comes from the one we just proved right up here. Alternate interior angles theorem. Boom, those two are congruent. We know this. So, we can write that angle 3 is congruent to angle 6 by our alternate interior angles theorem, or theorem. Alternate interior angles theorem. That's why angle 3 is congruent to angle 6. Now, angle 5 and angle 6. Oh, I'm going to have to rewrite that. I ran out of room. Generally, you write what's given in the first line, but there are times when you're using what's given later on in the proof and you can write it then. And I would say that from the diagram, angle 5 and angle 6 form a linear pair. After all, they're telling us this is a straight line, and they're cutting it with another line that automatically forms a linear pair. So I would list that as given. But the next one we actually have to cite a theorem, and that is that the measure of angle 5 plus the measure of angle 6 equals 180. And that's from a previous section where we noted that linear pairs are supplementary. Linear pairs are supplementary. We proved that in a previous section. Okay, we've got that these two are supplementary. We're trying to show that angle 3 and angle 5 are supplementary. How do we do that? And I probably should have written that right here, shouldn't I? Like I said, it never hurts to write down what it is you're trying to prove so that you always know what it is you're heading towards. So we have that these two are a form a linear pair, and it's angle 5 and angle 6. They add up to 180. On the other hand, angle 3 and angle 6 are congruent, so I can say that the measure of angle 3 equals the measure of angle 6. And why? Well, definition of congruence. Okay, if I do that, then I can write the measure of angle 5 plus measure of angle 3 equals 180. Why? Well, substitution. That's the substitution, well, you call that's a property of equality because we're using equalities here. And now I think we can write our QED. These two are congruent. That's from the alternate interior angles theorem. Angle 5 and angle 6 form a linear pair. That's given from the diagram. Angle 5 plus angle 6 equals 180 degrees. That's because we've already shown that linear pairs are supplemental. Measure of angle 3 is equal to the measure of angle 6. That's just from the definition of congruence. We already know they're congruent. Now we're just writing down that their measures are equal. And since we have an equality here, we can now use our substitution, put it in here, and we have what we really wanted to show, because that's the same as being supplementary. I suppose we could write one more line and say angle 5 and angle 3 are supplementary from the definition of supplementary. It seems so redundant, I'm not going to bother. So there we have it, all three of these proven fairly easily. This is not really earth-shattering stuff. It's just things that you need to know. And like I said, this is definitely not a two-column proof, but it's an easy way to remember it, and it's kind of convincing. I mean, once you lay this out, you can remember all of these results pretty easy. Well, here's one you probably don't even have to think about too much, if at all. A student concludes that angle 9 is congruent to angle 10 by the corresponding angles postulate. What did he do wrong? Maybe he asked the guy next to him. That's always a mistake. The other thing he probably did wrong was not notice that these two lines, they're not parallel. Remember, the corresponding angles, pardon me, the corresponding angles postulate requires that the lines be parallel. It's right there. They didn't capitalize it or italicize it or anything, but that's an important part. You can't just say two lines cut by a transversal. That won't work. They have to be parallel. These two aren't parallel, so the corresponding angles postulate simply doesn't apply. It has nothing to do with this. And here's one of those problems. They ask us to find x and y, and it looks more complicated than it is. At least I hope so. What we have here is interior angles. And more than that, they are consecutive interior angles, not alternate interior. Oh, pardon me. Anyway, we know that consecutive interior angles are supplementary. We just proved that a minute ago. So these two add up to 180, and these two add up to 180. I think that's how we should set up this equation. Although we're going to end up with two equations and two unknowns. We can do that. So we get 2x plus y plus 60 equals 180. And that gives us x plus y equals 120, or we could write y equals 120 minus 2x, like that. Why? Well, why not? Besides, we're going to have to solve for one variable in terms of the other in order to solve two equations with two variables. Although in this case, there is an easier way to do it, and I'll do it both ways. I'll start this way. And 2x plus y plus 40 equals 180 and I just corrected one of my bonehead mistakes. I wrote 2x plus y for the first equation. And the first equation is 2x minus y. That's obviously a minus sign there. I don't know what my eyeballs were looking at. So that works out to 2x minus y equals 120, and y equals 2x minus 120. Okay, so now this part's right. Let's get back to this here. Now this leads to 2x plus y equals 140. We have an expression for y right here. Why don't we just throw it in and see what happens? So we have 2x plus 2x minus 120 equals 140. Well, that should give us 4x equals 260, or x equals and we should get that x equals 65, I think. Wonder if that works. 2 times. Well, we haven't figured out what y is yet. x is 65. 2x would be 130 minus 120, which means y would equal 10. Now if we check that over here, we get 130 minus 10 is 120 plus 60 is 180. So it works out. So we get x equals 65 and y equals 10. But as I said, there's another way to do this. If you see it in the future, this might be a little quicker and more clever. If we write 2x minus y plus 60 equals 180. And here we have, pardon me, that's 2x plus y plus 40 equals 180. Suppose we add the two together. After all, if we had something like, if this was a equals, I'll write it right up here, suppose I wrote a equals b. Then I could add a to this side and b to this side, couldn't I? Yes, I could. You don't have to answer that. That's definitely okay to do. So, if I add this and add these two, what do I get? Well, the most important thing I get is that I lose the y's. I get 2x plus 2x, that's 4x. I get minus y plus y, that's nothing. And I get 60 plus 40, that's 100. And over here I get 360. So, that's 4x equals 260, which is just like what I had over here. It's going to lead to the same conclusion. X equals 65, and when I plug that in here, I will get y equals 10. This way here, if you spot that you can add these two together and draw and lose the y, you'll solve this equation quite a bit faster. If you don't spot that, then you're doomed to waste time like I did over here. But I had an excuse. I wanted you to see both ways to do it. I think I've mentioned before, there's more than one way to solve a math problem. Now here's one that's looks a little bit confusing at first. Just have to take it one step at a time and see what we're doing here. We have that angle 4 is congruent to angle 5. That may not be the first thing we use, though. What about SE, that's this segment here, bisects RSF, that's this here. Well, given that, we automatically know that angle 2 is congruent to angle 3. Okay. What else might we know here? Well, these two lines are parallel. See a little arrow they put right in the middle of it to let you know that, well, they're actually segments. We're not being drawn as lines, so we'll say these two segments are parallel. Here's a transversal cutting them. And this is a transversal cutting those same two parallel lines. So we may indeed make use of these, the fact that these are parallel, these two lines here, boom and boom, and that these two are transversals. How are we going to make use of that? Well, these are consecutive interior angles. I started to use something that's not quite true. Remember, this transversal extends off that way, right? Which means that this entire angle here so the supplementary pair between 3 and 4 would actually be this one here, which is not angle 3. It's this whole thing here, this. So we can't say that 3 and 4 are supplementary, because this is the extension of that parallel line, and this is the angle that would be supplementary to angle 4. That's the hard part of this problem, is keeping these transversals straight. Which angles are we talking about here? And which one is the actual transversal? But this transversal here, cutting these two parallel lines, means that angle 4 is congruent to angle 2 is congruent to angle 4. We know that because they are alternate interior angles. Now, let's look at this transversal cutting these two. Angle 1 and angle 5 are corresponding angles, aren't they? They form a corresponding pair. If I draw the two parallel lines over here, and then the transversal, this is the transversal here, and these are the two parallel lines here. So this is 5 and this is 1. You do it that way, it's more obvious that they are congruent. So angle 1 is congruent to angle 5. But wait a minute, angle 4 and angle 5 are congruent. So these two are both equal to something that is also equal, if that makes any sense. That's a dumb way to say it, isn't it? Somebody should pull me right out of here. No. I'm just trying to write this in shorthand instead of going through the whole thing, but yeah, I guess we'll just have to do it the long way. If angle 2 is congruent to angle 4, and angle 1 is congruent to angle 5, but, so I could write it this way. Now, I can just forget that line. We have angle 2 congruent to angle 4, which we know, because it's given, that angle 4 is congruent to angle 5, which, from this diagram, is congruent to angle 1. So, we can just jump right through the 4 and the 5 using transitivity and write that angle 2 is congruent to angle 1. But wait a minute. Angle 2 is congruent to angle 3. In other words, every one of these angles turns out to be congruent. They all have equal measure. Well, now we're almost done, because this is a straight angle. Remember, the parts add up to the whole. So angle 1 plus angle 2 plus angle 3. Now let's write it out the long way. Measure of angle 1 plus measure of angle 2 plus the measure of angle 3 equals 180. But they're all congruent. It means they all have equal measure. So just pick one. Let's say angle 1. The measure of angle 1 times 3 equals 180, or measure of angle 1 is 60 degrees. And we did that by spotting transversals and attempting to keep straight which are the angles formed by the transversal cutting the parallel lines. Because in a diagram like this, it does get confusing, because we got two transversals, and some of these angles are actually the angle formed by the two transversals, not the transversal and the parallel. In other words, angle 3 here. This is this transversal and this transversal. It's not this transversal and then the parallel line here. That would be a much larger angle. through so many steps, and that's the main reason it looks confusing. And it's the reason I had to stop and think about what the heck I was doing. And I might not have if I had done what I told you to do, which is prove. Well, in this case, we weren't really proving anything. We're finding the measure of angle 1, and that's already written, so I guess that wouldn't have helped much. Well, some problems just take longer, I guess. I can't give you a way to spot or a trick that would have made this any quicker. You just have to kind of recognize that it's getting confusing because we've got two transversals. And the complicated part is keeping straight what is the angle between the transversal and the parallel, and what isn't. Other than that, wasn't that bad, I guess. And that's it for now. Next time we're going to show how to prove that lines are parallel. That probably doesn't thrill you right down to your socks. But right after that, we're going to study slopes. And those are important. You're going to use them from now until the end of your life. Well, maybe not really, but you're going to use them in the rest of your math classes anyway. And I think I mentioned before, you can actually make money if you understand slopes. Making floor plans, site plans. These aren't, hardcore blueprints. You don't have to study drafting to be able to do this. Site plans are actually fairly easy to do if you pay attention in geometry class. You might be able to pick up a few bucks here and there drawing